Hi, class. This is a little video about what we've done in physics this week on Monday and Tuesday, October 26th and 27th. I realized that when I was doing this on the board the first time, I spent way too much time focusing on the math, and I want to pull back that focus because it's really the thought process I want you to get at when we're working these kinds of problems. We're going to use this kind of thought process more and more throughout the year, and I think this is just kind of a good practice to get us going in that direction. Our tests and quizzes will not be anywhere near this complicated at this point. Later on, we'll get a little bit more complicated. I'm going to ask you to do a couple steps, but I got to give you some practice and training to get there. So today I want to focus more on, again, the thought process as we're going through. So this is about the challenge problems I put out there on kinematics. If you look at the top of the screen here, I've got a whole bunch of equations that we can use to help us out as we're solving these things. Right, we have our definitions of what does a delta mean, right? That means change in. We take our final value of a variable, subtract its initial value. Got our two longer kinematic equations over here, right? And a couple other miscellaneous ones, right? These are definitions for V, definition for A, and two other little definitions for the average velocity, depending on how we're doing. Okay. So let's focus on how we're going to use these problems, or these formulas in our problems. So the first thing I want to look at here is, let's look at this first problem. And I've got it color-coded. So let's look at my note here first. Right, first, I want you to note there are two parts to this problem, The first part deals with the first 2 minutes, right? As the train pulls away from the station, starting from rest and undergoing a constant acceleration. After 2 minutes, the train has gone a distance of 310 meters. So that tells us our first part of our problem. We're going to use some information from this first part to help answer the second part, but they're distinct parts. And the reason I'm saying that is because the equations we're going to use are going to be distinct. They're separate for both. Right, so anytime I'm going to be using something from this first part, I want to use the subscript of 1, as you see here. So like I labeled in the problem that after 2 minutes, above that there's a little delta t, and I put a 1 after that t to indicate that's the change in time in scenario 1, part 1. Similar with our delta x here, delta x1, that's a change in position, that's our displacement for part 1. The second part of our problem here I've highlighted in blue. This is from 2 minutes to 22 minutes. Corresponds to this part here. How far will the train travel over the next 20 minutes, not including the first 2 minutes? And I will use subscript 2 for those. As we see here, delta T2 underneath the 20 minutes. So I want to go through here, now that we've separated it into the two parts, let's go through and label what we have. I've got them in here, starting from rest. Oh, I lost a V0 here someplace, so let's put a V0 in here, a V0, and this is going to be scenario 1. Right? So starting from rest, so that tells us our V01, right? It was 0. Undergoes a constant acceleration. We have it 2 minutes. That's our delta T1. So here we go. We've got our delta T1. We have a delta X1 here, 310. We've listed that one here. The only other information the problem gives us is our delta T2. So I've gone through and we've labeled all of our variables that we can. Let's do these in pink. Right there, in there, in there, in there. Right? So we've labeled the 4 that the problem gives us. Now, the next step, I want to be very clear. What is the problem asking you? What is the problem asking? Make sure you understand that part because it helps to know where you're going. Right? The problem is asking us, how far will the train travel? So that's our delta X2. So we're looking for delta X2. That's just kind of the setup of our problem. We need to get that basis done. So the only thing we know about part 2 is this delta T2, for example. See, we only have 4 variables. The only part we know is delta T2. So there's some information we're going to need to know from our part 1 that we're again going to use as we answer part 2. What are we going to use? What can we figure out from part 1? Right? We have our initial velocity. We have our change in time. We have a change in position. Change in our displacement. Right, so we can plug these numbers in, right? If we've got these 3 values, here's an equation that we can use all three of those values in. Right? Look at our equation, xf, x0. Well, we subtract those. That's our delta x. Good. We know v0. We know a. I'm sorry, we don't know a. We know t. We know our delta t. It's 2 minutes. So we know everything here except for the a. So we can use our initial data from our problem and this equation, and we can find the acceleration. That acceleration is going to be really helpful if we want to find. We're going to use that along with our delta x2 in the second part of the problem to answer. I'm sorry, we're going to use that along with our delta t2 to find our answer for our delta x2. All right, so I just manipulated this equation, this xf equals x0 plus v0t plus 1/2 at squared. And I'll leave that part of the math to you if you want to explore that. But it's going to come to this, a equals 2 times the quantity of delta x minus v0t divided by t squared. So let's plug in our values that we have for our problem here. Right? Our delta x is 310. Our v0, though, is 0. So that whole term here falls out. And then our finally at the bottom here is just our 2 equals 2 minutes squared. So you just punch that in your calculator. What your calculator is going to tell you, 155 meters per minute squared. Notice we have that minute squared in the bottom. Let's keep that square with our unit. We have minutes squared as our units. So A, we've got something now that's really helpful if we start to analyze part 2 of our problem. Part 2 of our problem. If we know A, then we can find V. Oh, that should say V at any point in time. If we know our A, we can find our V at any point in time. Now, our second part of our problem, it starts at V equal at 2 minutes and ends at V equals 22 minutes. So let's figure out what our V is for both of those times. And then once we know our V, that corresponds to our V final and our V initial of our part 2, then we can use those two velocities along with our acceleration. And here's a nice one of our kinematics equation that'll help us find delta x. So how do we find velocity 1 or velocity at 2 minutes? Well, we take our initial velocity, we take our acceleration. What do we see there? Our initial velocity was 0. Our acceleration was 155 meters per minute squared. How long are we accelerating? Well, we're looking for the velocity at time equals 2 minutes. So I'm going to put a 2 minutes in here. Now we're going to see that our velocity at 2 minutes is 310 meters per minute. That's important because that's the beginning velocity of part 2. V22, we're looking at the velocity at 22 minutes. Again, we're looking at our V0, that's 0. We have the same acceleration. And we've been going for 22 minutes, we've been accelerating. So now we know that our velocity at 22 minutes is 3,410 meters per minute. Awesome. Now again, right, in part 2, it starts at 2 minutes and ends at 22 minutes. So this first number here, this is our initial velocity. This guy's our initial velocity. And this one's going to be our final velocity when we plug things into part 2. So what do we know about part 2? We want to go back to this equation up here, this Vf squared equals V naught squared plus 2a delta x. Again, I did the manipulations here. If you want to, you can do the math to find that out. Again, I want to show the physics here, and I'm not going to focus on the math. Plug in our values that we just calculated, the 3410, the 310, and again, we know our A from as we did before. So we got this information all based on finding the A from part 1. Plug them all in, we get an answer of 37,200 meters. Again, my focus here is on the thoughts, not necessarily the math. Right? Realize that there's 2 parts to our problem. Let's separate those out, and we can use them as we attack to find our answer. Right? What do we know? Let's label our variables. What is it that we know? V01, delta T1, delta X1, delta T2, and make sure we're clear on what we're looking for, delta X2. Right, so we know there's something from that first scenario, that first part that we're going to use in our second part. What are some things that we could use? Right? We know our velocity, we know our time, we know delta x. It'd be nice if we could figure out what our A is, because we know it's going to be accelerating in part 2 as well. So we realize we can use one of our base kinematics equations. We can rewrite this and solve it for A. That's nice in this particular case because our V0 was 0. So our calculation becomes really simple. This was really important. Finding the acceleration was really important because we get a wealth of information about what's going on in part 2. Right? Once we know the A, we can find our velocity at any point in time. specifically the velocity at 2 minutes and the velocity at 22 minutes, because our part 2 starts at time equals 2 minutes and ends at time equals 22 minutes. Because once we know the velocities, we already know the calculation, we already know A, then we can use our other kinematic equation and we can solve that for delta x, right? So I just went through here, guys. Let's use we calculated our V at 2 minutes, our V at 22 minutes, and we could plug them into our delta x equation, and voila, out falls our number. So again, I'm trying to avoid the math here and just explain the thinking. Let's look at our second problem. Oftentimes I find drawing a picture is very helpful. So this time I drew a picture of our problem. So we got Bob is jogging along a straight path at a constant speed of 2.7 meters per second. So down here I've got Bob and he's moving at 2.7 meters a second. Let's continue on in our problem. Unbeknownst to Bob, 2 squirrels are fighting over an acorn on a tree branch 20 meters above the path he is running on. All right, so there we go. There's our 20 meters above the path. As he approaches the point on the path directly below the squirrels, but is still 10 meters away from this point, so he's still 10 meters away from the tree, the squirrels drop the acorn. So I want to indicate here, Bob is 10 meters away from the tree. That's when we start our scenarios here. He's 10 meters away from the tree. And the squirrels drop the acorn. Will the acorn, so our question now is, will the acorn hit the ground in front of Bob? And if so, how far in front of him? Hit the ground behind Bob? If so, how far behind him? Or will it hit Bob in the head? So like I said here, let's draw the picture and just start labeling what we know in the picture. It's very helpful to get our thoughts organized and keep things straight. So again, if we look at it, we're asking, where is Bob? Where is Bob? So we need to figure out where Bob is so we can tell if the acorn is going to land in front of him, and then how far in front of him, land behind him, or hit him on the head. So we need to know where Bob is when that acorn hits the ground. Well, that means we need to know how long it takes the acorn to hit the ground. So again, we have 2 parts to our problem, right? First one, how long does it take for the acorn to hit the ground? Right? How long does it take the acorn to hit the ground? Let's do that highlighter. Let's do this highlighter in, what did I say, yellow? Yep, in yellow. So the squirrels, they're 20 meters above the path. Well, that's not the color I wanted. Our squirrels are 20 meters above the path. Well, that's our x1, x1 being our part 1 scenario, and that's the initial velocity, right? I'm sorry, our initial position is 20 meters above the path. Well, what's the final position? That's when the acorn hits the ground. So I'm going to label in my problem x1f. It's our final position in scenario 1. What else do we know about scenario 1? Not much. We know that the squirrels are dropping the acorn. So what's that tell us about the initial velocity for scenario 1? It means it's 0. So those are the 3 things we know. We also know it's falling and it's using the rate of gravity, acceleration due to gravity, to pull it down. Well, what's the second problem? The second problem is, how far does Bob jog while that acorn is falling? Right? How far does Bob jog while that acorn is falling? Why is this giving me a different thing? How far does Bob jog? And we'll highlight that one in blue. Right? So how do we know that? We know that Bob's got a constant speed of 2.7 meters per second. So there's our V2. It's not even changing, so I'm not even going to talk about an initial or a final, just it's V2. What's our velocity in part 2? What else do we know about Bob? That's pretty much it. This part here about the tree, really is for the last part of the problem. We're trying to figure out where Bob is in relation to that acorn. So let's go through and let's start looking at our problem. Want to label, what is it that we know? And here I've indicated we know our initial and final positions of our acorn, right? It was 20 meters up in the tree, and it's going to hit the ground. So we know our initial and final positions. What do we know here? I really should have put this as V2, or our V1i. We know what's the velocity of the acorn when it starts. It's 0. They dropped it. What else do we know? We know our velocity in part 2 of our problem. And we know the distance to the tree that Bob starts out at. So that's what we know. Let's start plugging things in. We placed labels on our problem, right? We know our V2, we know our X1I, we know our X1F, our V1I, and our tree. So we've labeled our problem. Awesome. We also know that gravity, right? We also know that gravity is, let's do it this way. We also know that gravity, the acceleration of the gravity is negative 10 meters per second squared. So again, what is it that we can do? Let's go back and let's always, this is a great place to start this first equation. Do we have enough information to do anything with this? Well, absolutely we do. We know XF, we know, which is 0, the acorn hit the ground. We know X0, the acorn was 20 meters above the ground when it was dropped. We know V0 was dropped, it wasn't thrown. We know 1/2, we know A due to gravity is negative 10. Right, so we can just plug in our numbers. What's this going to give us? 20 meters minus, well, this first term's going to go, this middle term's going to be gone, right? It's got a 0 here. 1/2 times negative 10, that's going to be a negative 5. So we got 20 meters minus 5t squared. Rearranging, we got to rearrange our equations here. We're going to divide some things through, right? 20 minus 5, we divide, put the 20 on the other side. 20 equals 5t squared. Get rid of the 5 underneath the t squared. We're going to get t squared equals 4s squared. So that's just a manipulation of what we see in this equation here. Fine, that's real easy then. That gives us a nice number. We know that our t is 2 seconds. So we figured out that our acorn is going to take 2 seconds to fall. Again, what's our process? What do we know? And then what is it that we can find out from that? We needed to know the time that the acorn was falling. We figured out what variables we knew. We could figure out what problem to plug it into, and away we go. Now that we know the time that the acorn fell, now we can focus on the second part of our problem. How far does Bob get in those 2 seconds? Well, that's not too bad. We know our position is equal to our velocity times time. The problem gave us our 2.7 seconds as our velocity. So if he's running for 2 seconds, how far does he get? So if he moves 5.4 meters in those 2 seconds. Well, if the acorn was originally 10 meters in front of him, and he only went 5.4 meters, where's the acorn going to land? 10 meters minus 5.4 meters, it lands 4.6 meters in front of him. Again, when we look at this problem, what is it I want you to see? I want you to be able to break it into parts. What's part A, part 1, and what's part 2? Let's look at the variables that it tells us. Right? Part 1, how long does it take for the acorn to hit the ground? Part 2, how far does Bob jog during that time? And then we just set about doing our calculations. Right? We want to find how long it takes for the acorn to fall. We look at all the variables we know about part 1, and we realize we can use our main kinematic equation, plug our variables in, solve it for the time we're looking for. We get our time, 2 seconds. Not too bad. Now that we know our time, it's real easy to go into part 2 of our problem, use that with the velocity in part 2, and we can figure out the distance that Bob traveled. This is the thinking I want you to do. So I was trying to minimize my focus on the math here. Focus on the thought process, guys. Focus on the thought process. Hopefully you found this helpful. If you do have questions, please email me. I'd love to help clarify anything that doesn't quite make sense yet. Thanks, guys.